my name is Tally, and I am an intern at the Science Squad Corporation. Today, we have Dr. Joshua Tan from LaGuardia Community College in New York, talking about his work in neutron stars.
Okay. Well, thank you very much. My name is Dr. Joshua Tan. I am a professor of physics and astronomy at LaGuardia Community College, which is part of the City University of New York, and also a research associate at the American Museum of Natural History. What I study is neutron stars, and stars generally. And I have a picture here of some stars that I might be interested in studying. It's an artist's conception of two stars that were born relatively close to each other. And because of this, they're actually dancing around each other in an orbit. Just like the planets orbit our own sun, if two stars are born relatively close to each other, they end up orbiting each other. You don't say that one is the center and the other is the center. It's actually more of a dance. But what I'm interested in is when we have very massive stars, stars that are much more massive than our own sun, and then something like this occurs. This is a so-called supernova. Supernovas occur when we have very massive stars, much more massive than our suns, that explode in rather violent explosions that can then be seen essentially across the entire universe. These explosions are so bright they can outshine all of the stars in a galaxy being essentially billions and billions of stars. So thinking of having a star that's much, much brighter in an explosion than any one given star might be over its entire lifetime. After this explosion happens, you might end up with something that artists might conceive of looking like this, right? Where we would start off with a red giant star, one of these big stars. Then there's this explosion that happens, and what's left at the end is this thing called a neutron star. And I get interested in these neutron stars, these tiny remnants, these cores left over that have been squashed down to incredibly high densities, and may show us some interesting things about the way nature behaves, because it's matter under extreme conditions. This is what neutron stars are approximately like in size. So here we have New York, and compared to New York, here's a neutron star. You can see it takes up about the same amount of space as New York. But a neutron star would have more mass than our entire sun. So that's why we say they're so incredibly dense. They're just squashed down versions of stars. And because they're so extreme, we can actually see them from different parts of our own galaxy, different things that they do give us information about the neutron stars. And that's some of the things that I'm interested in. This is a picture of what neutron stars' characteristics might be like. Neutron stars spin around, and they develop something called a magnetic field, similar to our own Earth. The reason that compasses go north, point north on our Earth, is because the Earth has a magnetic field. Well, neutron stars also have a very strong magnetic field, much stronger than our own Earth's. And that magnetic field actually allows for radiation to beam out in various directions away from the neutron stars. And if we see that radiation, we'll actually see it flash on and off, sort of like a lighthouse. That's because as the neutron star spins around, that radiation will sometimes be pointed towards us, sometimes away from us, and when it's pointed towards us, we see this great signal from the pulsar, which is one of the things I'm interested in. But as I said, there were actually two stars to start off. So what happens with that second star? Well, sometimes it's pushed away, but sometimes it's not. Sometimes it sticks around. And when it sticks around, a situation can happen like the one I'm showing here in an artist's conception. So a situation where material from the star that didn't explode is now being pulled off by the gravity of the neutron star. It forms something like a disk as the material falls down. The neutron star, some very interesting things can happen, and we can see some interesting types of behavior from the neutron stars, as well as the material spiraling around in the disk around them. So I've gotten interested in these sorts of objects as well. They're called binary, X-ray binaries, because a lot of the light coming from them is coming in the form of X-rays. Another type of thing I get interested in is different sorts of neutron stars that pulse this radiation that I will then see in the radio part of the spectrum. And I'll give you a sense for what a radio telescope might see for different pulsars. So this is a normal pulsar, right, that has just a pulse happening every once in a while, about once every second. And those pulses are happening because that radiation beam is pointing towards us once every second as the whole star spins around. It's really quite a fun thing to think about, that we're getting information about how the star is spinning. This is a somewhat faster neutron star. This neutron star is spinning once every fifth of a second, or 5 times a second is another way to say it. And so you can see that those pulses are happening much more rapidly. This star is spinning around much faster, this neutron star. And so I've gotten interested in the stars that spin the fastest. And in the situation where you have a star that has given some of its material to a neutron star, it'll actually cause that neutron star to spin as fast as possible. And this is the example of a neutron star that spins as fast as possible, what its signals sound like. We hear like a hum, and that hum is happening because we can't make out individual pulses anymore. Now we're hearing the sound that a lot of, maybe hundreds of pulses put together, sound like to our ears from those vibrations. It's called a tone. These are so-called millisecond pulsars, and they're the things I'm interested in. The pulsars that have been in binary systems and that have spun up to this high speed. This is an artist's conception of what that might look like. A millisecond pulsar that has been spun up and now is spinning so fast it's actually disrupted the disk of material that came off of the star that it is in an orbit around. And so you might get interested in the millisecond pulsar itself in these binary systems, but you can also get interested in the star that's next to them as well. So this is sort of the view that we have. You've got this neutron star, which is really small and really strange and hard to see. And then right in the neighborhood, right next to it, we see one star that might be very similar to our sun. But this star may have some characteristics, some features, some things that happen to it that may cause it to be very different from our sun, very different from other sorts of stars that we might see. In fact, we might see some features of the dance that this star does around the neutron star. How could we observe some of these things? Well, one way we do it is we look through space telescopes. So one of my favorite space telescopes to use to observe these things is called the Fermi Gamma Ray Space Telescope. Fermi Gamma Ray Space Telescope is very sensitive to high energy radiation that could be coming from these systems, and in particular millisecond pulsars, the ones that we saw that were rotating very rapidly, often are very visible using this telescope. So this is one way that we might study them. Another way we could study them is using radio telescopes. So that's how we get those pulse informations. This is a radio telescope in Australia that we've gotten data from. It's called the Parkes Radio Telescope. It was made famous in a movie called The Dish, which I suggest people go check out. It's about 20 years old now. The way I often look at these systems, however, is using regular optical telescopes. And this is one that I've used quite a bit. It's on Kitt Peak in Arizona. It's a small telescope by comparison, but it actually has a mirror that's 2.5 meters across. So that's small by other comparisons, but it's pretty large compared to the normal telescopes that people have in their backyard. This is what the control room looks like, where I did most of the data analysis that I worked on. And I looked at a couple of these systems. We can only see, using these optical telescopes, the companion star. And so I'll show you a picture of one that I discovered. It's a little bit hard to see here. What you see is 2 different pictures taken at 2 different times. And in one side of the picture, we can see some of the stars, and on the other side of the pictures, we can see the same stars, but there's one star that's very bright, or at least relatively bright, on the left, and then it looks faint on the right. So I'll leave it to you to see if you can figure out where it is, but I'll give you a hint. It's right next to one of the brightest stars in the image. So there's a very faint star that's right next to one of the brightest stars in the image, right to the left of one of the brightest stars of the image, that looks faint, but is pretty bright on the left, and then almost disappears on the right. And that happens to be the companion of one of these neutron stars that I've gotten interested in. To show you a little bit better how this works, let me show you a movie of a different neutron star that you can see get bright and dim over the course of a few moments. So here you can see it get bright, and then it gets dim, and it gets bright, and it gets dim. And it's doing this because it's dancing around a neutron star, and that neutron star is heating it up. And when we see it heated up on one side, it looks bright, and then on the other side, it's a little bit cool, and so then it looks dim. And we follow it over the course of the dance that it's doing around the neutron star. So this is the sort of thing I've gotten interested in, because I got really interested in trying to figure out what the neutron stars are doing to their companions. And just to kind of show you the work that I do in looking at these things and trying to figure out how this works, I'll show you an artist's conception of what that might look like. So you can see that star is being very, very distorted by the neutron star, but also it's become very bright on one side and very dim on another, and even has material that's being pulled off of it in multiple directions. You kind of see these weird wispy disks that are coming off of it. So this is essentially what I study. This is the sort of work that I do. I'm extremely interested in looking at these neutron stars and their companions. The hope is that we might learn something about both of them and try to discover some of the weird things that can happen out in our universe. So thanks very much for listening to what I have to say, and I hope you enjoyed my discussion.
Thank you, Dr. Tan, for presenting, and thank you all for listening. Make sure to subscribe and watch out for our monthly lecture series where we bring in experts in STEM fields to discuss their work.